Non-destructive testing, X-ray inspection and industrial computed tomography. X-ray inspection and computed tomography are widely used in many areas of everyday life. Their application is best known in medical imaging. Using X-rays, medical doctors can visualize the interior of the human body. Even complex structures can be made visible. But X-rays are not only used as a diagnostic tool. They also contribute to our security, for example at the airport. At the security gate, each piece of luggage is examined by X-rays, also the suitcase. The X-ray image of the suitcase looks like this. Various objects can be identified. An alarm clock, a pair of glasses, a hairdryer, a trouser hanger, a pair of shoes, and many other items. In contrast to conventional X-ray images, here the objects are displayed in colour, according to their specific material. This is made possible by distinguishing between low-energy and high-energy radiation. Metallic objects are displayed in the colour blue, certain non-metallic items in orange. In this way, it is easier to detect dangerous objects. X-rays are frequently used in non-destructive testing of materials as well. The inner contours of complicated workpieces can be made visible, and of course defects, such as cracks and pores. But how are X-rays actually produced? They are generated in a so-called X-ray tube. To build an X-ray tube, first of all a thin-walled glass tube with a high vacuum within is needed. In the lower part of the tube, a V-shaped wire made of tungsten is positioned. This is the so-called thermionic cathode. A cylinder with an inclined end face is located in the upper part of the tube. This cylinder is the anode. It is made of a refractory metal that conducts the heat well. From a high voltage source, the positive pole is connected to the anode, and the negative pole to the thermionic cathode. The thermionic cathode is now heated up by an electric current. The thermal movement enables some electrons inside the wire to leave the surface. This is known as thermionic emission. By switching on the high voltage, a strong electric field between the thermionic cathode and the anode is created. This strong electric field accelerates the emitted electrons towards the anode. An electron beam is formed. The electron beam collides with the anode at high velocity. The anode material slows down the electrons within a very short distance. This generates the desired X radiation, but unfortunately also a lot of heat, which has to be dissipated by cooling. Because the anode surface is slightly inclined, the emission of the X radiation towards the right is more intense, but a certain proportion also radiates in other directions. A protective housing shields X-rays going in unwanted directions. The desired X radiation can only reach the outside through a small transparent window. With this setup, a high-resolution X-ray examination is not yet possible. The problem here is the large area on the anode where X-rays are generated. The X radiation is too diffuse, so a fuzzy and low-contrast X-ray image would be the result. To solve the problem, an electromagnetic lens is used to focus the electron beam at a small spot on the anode surface. The smaller the focal spot, the sharper and higher in contrast the X-ray image will be. Now, how are X-ray images actually produced? For an easier understanding, we will first depict the usable X radiation as a grey cone, and then simplify it as a parallel beam. To take an X-ray image, a suitable image capture unit is needed. This can either be a conventional X-ray film which turns darker the higher the intensity of the radiation, or it can be a digital detector field that measures the intensity of the radiation and converts it to electrical signals. When the radiation intensity is plotted as a function of the position, a uniform distribution is the result, as shown here. At each point, the image capture unit records the same radiation intensity. But what happens to the diagram when a material sample is placed in the radiation path? The sample absorbs part of the X radiation. The principle is, the thicker the sample in the direction of beam propagation and the higher its density, the less radiation reaches the image capture unit. Defects such as cracks or pores absorb very little radiation. Therefore, places with defects lead to higher radiation intensity at the image capture unit than flawless places. Defects extended in beam propagation direction can be seen particularly well. Those defects which only have a small spatial extension in beam propagation direction can hardly be seen, or cannot be seen at all. And this is what the complete X-ray image of the sample looks like. The originally depicted sectional plane of the sample is shown as a dashed line. Places with defects appear darker because a more intense radiation reaches the image capture unit. As expected, the vertical crack is virtually undetectable. This X-ray image is only obtained with parallel radiation. Using a classical X-ray tube, however, the radiation is cone-shaped. The intensity distribution will therefore look different, and as a consequence also the X-ray image. The edges of the sample now appear three-dimensionally and not as clearly outlined as before. But now there is another problem. The position of the defect and depth, that is, in beam propagation direction, cannot be determined with a single X-ray image alone. It hardly makes a difference in the image whether a defect in the sample is positioned further to the left or to the right. In order to determine the depth of location of a defect, at least one additional X-ray image has to be taken from a different direction. Computed tomography pursues exactly this approach, not only by taking one, but in fact many additional images. A fantastic method. How does it work? The aim of industrial computed tomography is to create a three-dimensional computer model of the sample. To explain the principle, we are going to examine a simple rectangular aluminium specimen. It is placed on a rotating sample stage. Various saw cuts and drill holes have been machined into the specimen. The X-ray tube is located on the left side. The detector field is on the right-hand side. In step 1, the computer tomograph records one X-ray image after the other and saves it. After each recording, the sample stage rotates the specimen by a certain angle. In this way, many individual X-ray images from different directions are captured. In contrast to medical diagnostics, the X-ray tube and the detector field are both at rest, and the sample rotates. The X-ray images are displayed in real time on the computer monitor. As opposed to classical X-ray images, they are shown as positive images. Thick areas and areas free from defects now appear dark. Thinner regions or regions with defects appear light. The drill holes and the different saw cuts are clearly visible. After all the X-ray images have been taken, step 2 follows, the generation of the computer model. This step is called image reconstruction. For image reconstruction, several useful methods exist. Here we will explain a commonly used method, the filtered back projection. A specimen with a cube-shaped cavity is used here as an example. To demonstrate the principle, we will explain the back projection of a sectional plane that goes through the cavity. The sectional plane looks like this. After having taken all X-ray images, the distribution of the transmitted X radiation is projected back into the sectional plane. This process is repeated for each X-ray image and the distributions are superimposed. With each superposition, the quality of the model increases. Displayed as a positive image, the back-projected plane looks like this. Much better results can be achieved with appropriate filter methods and with even more images. The back projection is carried out successively for each sectional plane, until finally a three-dimensional model of the sample is generated by the computer. Using sophisticated visualization methods, the sample can be examined in detail on the computer display. This is the computer model of our aluminium sample. Not only can it be viewed from the outside, a look at the inside is also possible by means of various sections through the specimen. The first drill hole, the second drill hole, the saw cuts, and the third drill hole. And here we go. We want to examine part of a die-cast sample made of an aluminium alloy. Shortly after the start, the first X-ray images can already be seen on the monitor. After recording one X-ray image, the sample is rotated slightly and the next image is taken. The resulting X-ray image files are also called raw data sets. Later on, the raw data sets enable a reconstruction of the individual cross-sections and, based on them, the calculation of the computer model. Now the computer model is completed. The inside of the sample can now be inspected in detail, and above all, the method is completely non-destructive. Many pores of different sizes can be seen. The pores are filled with air that has been trapped in the course of the die casting process. The venting of the die has not been good and has led to a great number of large air inclusions. If preferred, the material can also be visualized transparently. Then the defect surfaces appear bright. The following image shows an enlarged section of the sample in red-green technology. With ordinary red-green glasses, the pores in the interior of the material can also be experienced in 3D. Computed tomography is a fantastic method, so it is not surprising that it is being used more and more as an excellent non-destructive testing method in materials testing.